Okay, let's continue on. We're just going to quickly recap um, the last time when we talked about why we wanted to talk about just the first 20. Um, we said living things are composed of these simple common atoms. Remember, 95 to 98% of the body is made up of 6 common atoms, and we know that those 6 common are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and we call those chnops. And just to refresh you of those names, okay? All right, so let's look at molecules. Think about it. We know that atoms are rarely found singly in nature. Okay, they are found as who? Molecules. So that's the usual form that you find atoms in. They've already combined it there in molecules. So the question is, why would these atoms be rarely found singly in nature, but otherwise found as molecules? Well, we know that they are seeking to fill their outer electron shells. And so in order to fill their outer electron shells, we know that they must interact with other atoms. And when they interact with other atoms, we know that they're going to form chemical bonds. So let's look at those outermost electrons, because it says here that valence electrons, which are the outermost electrons, they determine reactivity. So how do we know that something's reactive or non-reactive? So, well, something's reactive if we know that the outermost shell isn't complete. We have fewer than the number of electrons that are allotted. So in other words, if the atom only has one shell, okay? If the atom only has one shell, then we know that, for example, in the case of hydrogen, remember hydrogen had one proton, and then it had one electron. So that one shell is not complete because we know that it can hold 2 electrons. So that one would be reactive if it had more than one shell, for example. Say, for instance, if we were looking at sodium. Sodium has 11 protons, and my pen tried to sneak away. Has 11 protons, has 12 neutrons. The first shell will hold 2 electrons. The next shell will hold 8. 1, 2, 3, 4, 5, 6, 7, 8 electrons. And then the last shell is going to hold 1 electron. So we know sodium as well is reactive. Okay, let's go on to the non-reactive guys. So we know anything would be non-reactive if it has a complete outer shell. And so we automatically know that those noble gases that are in the column number 8 or group number 8, they all have the max number of electrons in their outer shell. So if we looked at helium, for example, we know that helium has, helium is number 2, has 4.0003. So this tells us that it has 2 protons, and we know since it's electrically neutral at this point, it also has 2 electrons and 2 neutrons. So we have 2 protons, 2 neutrons, and 1 shell completely full with 2 electrons. Okay? Happy, 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 not looking for love in all the wrong places. Okay? So let's continue on. Now, So what can atoms do with their electrons? We know that atoms can give up their electrons, they can accept or take electrons, but then what else can they do? Absolutely right. They can share their electrons in order to complete their outer shells. We know that when they have complete or full outer shells, we say that they are following the octet rule. So remember that. Remember from the other day, we said if they have complete outer shells, we said that they are following the octet rule. Okay? And so we know that all of this is important when we're talking about making chemical bonds. What are we going to do with the electrons? What do the rules say we're going to do based on what a particular atom has in its outer shell? All right, so it says there's 3 different types of chemical bonds, and we know that those are covalent bonds, ionic bonds, and hydrogen bonds. So we want to look at some information and some rules about how each of these bonds and how they take place. So let's begin with the covalent bond. Now, the covalent bond, we know the key phrase is to do what? It is to share a pair of electrons. And if we look at hydrogen, again, we've just used that little guy over and over and over again. You ought to know hydrogen. If you don't know any other atom, you ought to know hydrogen. All right, so if we look at the stats of hydrogen, it says hydrogen has one atomic number is number 1, which means it has 1 proton, and since it's electrically neutral, it has 1 electron, and then we know that the mass is like 1.007 or whatever. All right, so it says if we drew it, we know we'd have 1 proton in the nucleus, 0 neutrons in the nucleus, and 1 shell with 1 electron. So here we go. And one of the things that you'll see if we looked at hydrogen gas, H2, we'll see that if we are making a covalent bond, they are sharing this pair of electrons. And so you can see that these electrons are free to orbit about both nuclei. Okay, they're free to orbit about both nuclei. So this hydrogen needed 1 electron, has 1 electron. He only needs to add another one. This hydrogen has 1 electron. He needs 1 other. So it says that now both have complete outer shells because they both need what? 2 electrons. So these electrons are orbiting about both nuclei. Okay, we don't know what that extra line is. I didn't do that. All right, so let's keep going. Okay, another way that we can show hydrogen gas, we can illustrate hydrogen gas. So I'd already said that, but we can illustrate hydrogen gas with this solid line or solid bar between both atoms. Okay, so we said now on the previous screen we showed that the hydrogen's outer shells were actually overlapping and the electrons were orbiting about both nuclei. Remember that? And so, but now it says another way that we can illustrate this is just to simply take both atoms, and then this line represents the covalent bond between both atoms. So that represents a covalent bond. They are sharing a pair of electrons. We could also write it like this. We could say hydrogen, here's its electron, here's the other hydrogen's electron. So they're sharing a pair of electrons between the 2 atoms. All right, oxygen gas, slightly different from the first covalent bond, and only because we're going to be sharing 2 pairs of electrons. So first we got to get the stats for oxygen in order to draw it, And if you remember, oxygen is number 8. The mass number is 15.99 something another, so we just put 15.99. So we know that this guy has 8 protons, 8 electrons. If we round this to the nearest whole number, that's going to make a mass of 16. So we can calculate the number of neutrons by taking the mass number minus the protein number. So the number of neutrons is equal to 8. Okay, and that's about it. So we can draw each one of those. First shell is going to have 2. Then in the outer shell is going to have 6. He's going to need to share 2 from somebody else in order to have a total of 8 in the outermost shell. So what does the single oxygen atom look like? Looks something like that. Okay, 8 protons, 8 neutrons in the nucleus. Remember, we've got 2 electrons in the first shell, 1, 2, 3, 4, 5, 6 in the outermost shell. So if we drew the other oxygen, we would be actually sharing 2 pairs of electrons. So we're going to share this pair of electrons, we're going to share that pair of electrons. So look, that's 1, 2, 3, 4, 5, 6, 7, 8. For this guy, 1, 2, 3, 4, 5, 6, 7, 8. So it says each one of these now have 8 electrons in their outer shell. Alright, so we said slightly different. Why? Because we're sharing 2 pair of electrons. So we said that this oxygen shares 2 pairs of electrons. Okay? That represents those double lines. Okay? So if I asked you on a test, well, how many electrons are in a double bond? You tell me how many. 4 electrons are in a double bond. But what if I ask you, well, how many pairs do I share in a double bond? You tell me what? Here's a pair. Here's a pair. That's what? 2 pairs that are being shared. Okay? Alright, so this is just giving you some other ideas on covalent bonding. Alright, so it says, is it possible to have a triple covalent bond? Of course it is. It says in a covalent bond, we're going to share 3 pairs of electrons. So, in other words, if we looked at the formula C2H2, that would represent a a non-polar covalent bond. Okay, so this is the same thing. So if we had drawn hydrogen, which had 1 proton and 1 electron, and then go on and draw a carbon. Remember, the carbon is going to have 6 protons, 6 neutrons. First shell is going to have 2 electrons. This shell will have 1, 2, 3, 4. So here's that pair of electrons. Here's the other carbon. 1, 2, 3 with 1. Gonna have 6 protons, 6 neutrons. First shell is gonna have 2 electrons. So 4 in its outer shell. And then finally another hydrogen. Okay, which is gonna have 1 proton. And then in its outer shell, that 1 electron. So we're sharing a pair of electrons here. That's that 1, shared 3 pairs. And then finally, here's the last 2 pair. Okie dokie. Alright, so it says every bond that we drew before was a nonpolar covalent bond. And nonpolar covalent bonds means that they shared their pair of electrons equally. They share their pair of electrons equally. I'm going to end here because I know I'll go ahead and tell you what a polar covalent bond is. So then a polar covalent bond, we know that they share their pair of electrons unequally. So they share electrons unequally. And then we said, remember, nonpolar covalent bond, they shared electrons equally. All right, until next time, I hope you guys have a wonderful day, and I'll talk to you later. Bye-bye.